Welcome! In this video, we're diving into one of the very first steps your phone takes when connecting to a 5G network, the physical broadcast channel and the master information block. We'll explore what they are, why they're essential for initial access, and how they fit into the bigger picture of 5G communication. Then, we'll move from theory to practice, showing a MATLAB implementation that detects the PBCH and decodes the MIB from a 5G signal. Let's get started. In our previous episode, we explored the primary and secondary synchronization signals and saw how they help a device lock onto a cell during the initial search. Now we move to the final piece of the SSB, the physical broadcast channel. It takes up most of the SSB's resources, and it's the UE's gateway to learning how the network is configured. If we zoom in, we find that the PBCH isn't made up of just data symbols. It also contains demodulation reference signals inserted on every fourth subcarrier. These signals allow the receiver to measure the channel's response and correct any distortions before decoding the PBCH bits. The DMRS positions aren't random, they depend on the physical cell ID. There are 4 possible starting positions, calculated using the formula shown on the slide. Beyond helping with channel estimation, the DMRS also serve another important function. Their values allow the UE to determine the SSB's position within the half frame. As you may recall from an earlier video, SSBs are transmitted in short 5-millisecond bursts, typically repeated every 20 milliseconds. The PBCH DMR's values are generated based on the SSB index, which means the UE can perform a blind search across all possible indexes to identify the exact SSB position within the burst. Later in the video, we'll demonstrate this search in MATLAB and see the result in action. After equalizing the PBCH using the DMRS, the UE can finally decode its most important content, the master information block. It provides the system frame number and the subcarrier spacing used by common channels such as the PDCCH and PDSCH. It also tells the UE the SSB's frequency offset and the position of DMRs within the PDSCH, which are important for proper decoding of subsequent data. Additionally, the MIB includes CORESET and search space configurations for the PDCCH carrying SIB1, guiding the UE on where to look for system information. Finally, it indicates whether the cell is barred or if the UE can reselect to other intra-frequency cells, helping the device make correct mobility decisions. In the second part of this video, we'll continue building our MATLAB-based receiver from the cell search video, this time adding PBCH and MIB detection. If you haven't seen that video yet, we recommend watching it first or downloading the corresponding code using the link below. Our current receiver implementation already performs frequency and timing synchronization and retrieves the physical cell ID from each detected SSB. The next step is to extract the PBCH along with its demodulation reference signals and perform channel estimation. To accomplish this, we use a custom function. It returns the estimated channel, the noise variance, and the index of the SSB within the half frame. Inside the function, we first calculate the DMRS indices based on the cell ID. Then, we perform a blind search over all possible SSB indexes. Each index corresponds to a possible SSB position in the half frame and determines which DMRS set was used. We start by creating helper variables, DMRS estimate to store intermediate results, and a reference grid to hold symbols for channel estimation. Next, we loop through all possible SSB indexes from 0 to 7. For each index, we assign the corresponding DMRS values to the reference grid and perform channel estimation, producing both the channel estimate and the noise variance for that candidate index. To compare estimates across different SSB indexes, we calculate an SNR-like metric. This metric takes the average power of the channel estimate, divides it by the noise variance, and expresses the result in decibels. The index with the highest metric value is the most likely correct SSB index. Once the SSB index is determined, we can calculate the final channel estimate using the correct DMRS set. Since we already know the SSS values, we can also incorporate them into channel estimation. To do this, we calculate the SSS grid indices, assign the values to the reference grid, and perform the channel estimation. In the console output, you'll see the correctly estimated SSB index positions. These match the transmitted block configuration from the earlier SSB video. Since the signal contains 2 SS bursts, we observe 2 sets of repeating indexes in the output. In the next part of the code, we decode the physical broadcast channel. The decoding function returns a CRC checksum to verify whether the BCH contents were correctly decoded. It also provides the BCH transport block, the system frame number, and the SSB subcarrier offset. Before implementing this function, we define a variable to store the maximum number of SSBs that can be transmitted in an SS burst. Inside the PBCH decode function, we first extract the PBCH symbols using MATLAB's NR PBCH indices and NR extract resources functions. We then extract the corresponding symbols from the channel estimate and perform channel equalization using the minimum mean square error method. This produces the equalized PBCH symbols, along with channel state information, which reflects the reliability of each symbol based on its signal-to-noise ratio. Next, we calculate the number of bits per symbol, which is 2 for QPSK used in PBCH, and reshape the CSI to match the number of bits. We then proceed to demodulate the PBCH. First, we compute the scrambling sequence corresponding to the SSB index. Then, using MATLAB's NR PBCH decode function, we retrieve the PBCH bits and apply CSI weighting to improve decoding reliability. Finally, we perform BCH polar decoding. This step returns the CRC checksum, the transport block containing the MIB, the 4 least significant bits of the system frame number, and the MSB index offset, which is used to calculate the SSB subcarrier offset. In FR1, this offset is represented in multiples of 16 subcarriers. Next, we decode the master information block using the decode MIB function, which outputs the MIB in a readable format. This function relies on 4 components from the MATLAB NR Cell Search MIB and SIB1 recovery example: bit field, message format, MIB, and PDCCH config sib1. Be sure to include these components in your project folder. We start by extracting the MIB from the transport block bits using the predefined MIB class. Then, based on the frequency range, we define the possible subcarrier spacing values, 15 or 30 kHz in our example, and parse the MIB contents. In the console output, we can see the decoded MIB for each SSB. The first parameter is N frame, the system frame number. Next is the subcarrier spacing for common channels like PDCCH and PDSCH. The kSSB parameter equals 14, which differs from the value set in the SSB transmitter configuration because it also incorporates the NCR-BSSB parameter using the formula shown on the screen. This is followed by the DMRS Type A position and the PDCCH configuration for SIB1, which tells the UE where to locate and decode the PDCCH and SIB1. The next parameter, cell barred, indicates whether the cell is barred for access. If it's 0, the UE can connect. Finally, the parameter controlling intra-frequency cell reselection specifies whether the UE is allowed to reselect to other intra-frequency cells. In the final part of the video, we'll modify the channel model to observe its impact on the receiver. We'll introduce two elements: multipath propagation, a main signal delayed by 100 samples, plus a weaker echo delayed by 300 samples with a Doppler shift of 100 Hz and additive white Gaussian noise, adjusted to achieve a signal-to-noise ratio of 10 decibels. We'll also update the PBCH decode function to include a figure plotting the PBCH constellation after equalization. In the resulting plot, the QPSK constellation points are clearly visible, confirming that the MIB was successfully decoded. This indicates the receiver accurately estimated the channel effects and correctly equalized the PBCH symbols. And that wraps up our video. If anything's unclear, feel free to ask in the comment section down below. Thanks for watching.